All right, so we're trying to quantize gravity here. And we can do that if we take all the zeros that are here on the critical strip, the Riemann zeta function. And let's say, for example, that we do infinite transformations. So, these are the zeros here, but in this dimension, they correspond to these particular numbers. Okay, well, in the next situation here, they're just moving over. So again, these are going to be these numbers. So I'll put even a different color here. These numbers here. They are going to be popping up here. Okay, and then we can sort of do that over here and get some new color. And these zeros line up to these particular ones. Okay, these are just the zeros. And, obviously this is sort of the ideal transformation, but there are other ones. Well, what happens when other types of transformations happen? It's kind of strange what happens. Because what can happen is curl, you can curl the zeros and you can form, well, first let's describe what these zeros are first, I guess. These zeros actually quantum unique zeros. In fact, they have an imaginary component encoded into them, so that way they form this system of eigenvalues where the distances here are actually getting larger and larger. So this distance, and then it gets smaller and smaller. Interesting. Well, that is essentially acceleration happening. Yeah. There's different ways to think about this because these curvature lines are leading you towards something. You can follow the lines. Well, if you follow these lines, what happens is, uh, let's say we formed a sphere of, of zeros. Before we can form a sphere of zeros, first we have to form a circle of zeros because notice these are just points of zeros. So unfortunately, how are we going to create a sphere of zeros through the points? Well, we have to rotate, first of all, at the golden angle is the optimal way to do this. So let me just go ahead and take a look at statistics here. And let me pull that little circle out because this is kind of the optimal way to sort of distribute these points. So that's one dimension. All right, but clearly this could happen in some other dimension, and then you could fill in, say, the rest of the sphere with circles. This thing with circles. Sorry, this line, this whole line could be filled with essentially these unique zeros. Then you might have to intersect this, with different stuff. But then there's, going to be another, whatever. The idea is this forms a sphere. So, something like this, more. So the idea is that this forms a sphere of zeros. And all of these zeros are impossibilities. Impossibilities. Impossibility sphere. Hmm. So that way, all these things are just zeros. And they're unique zeros. Remember the very special, unique zeros that, you know, here they are. I'll even bring this thing over because the spacings are important. So if they're unique zeros, what that really means is that they're impossibility points. So, if the idea is that there's zeros and ones. That's really all there is. And, there's other numbers too, but they all sort of go into this little matrix over here, and we can call them the possibility matrices. So that this is the possibility matrices with all the other numbers, including a regular old zero. That can go in there too, because the thing is, these are just trivial zeros, so like, they don't contain an imaginary component. So like, all those zeros are essentially the same. And let's label these zeros here. These trivial zeros. Trivial zeros. They seem to be photons. Because all the photons are essentially the same. Over here, these non-trivial zeros, these appear to be gravitons. And so these appear to be graviton eigenvalues. Because they're all unique zeros. And so essentially there's like this shield of gravitons here. The impossibility sphere. All these unique zeros that are blocking off quantum information. So quantum info, you can't pass the quantum info through here because it's just going to get trapped by this wall. So the quantum info is essentially blocked here, and you can't pass the info through. And this seems to be what the black holes are. And the surface area is going to be the entropy. What was the surface area of the black hole again? It's like S equals some 4 pi area G, something like that. Oh, KBA over surface area. Surface area is equal to, I think there's a special, oh my god, was that a cat? KB, here's the area. This is black, yeah. And then we have divided by 4. I don't know what's happening. It's like all these formulas. Hold on a second. Let me find it. Here. 1 second. Wait. I guess it's 4 L squared. What the? Interesting. Length. Uh, A is the surface area. KB is the Boltzmann constant. L is the Planck length. Well, this might lead somewhere, but essentially, I just want to kind of give an update of where I was going with this. And the idea is that in order to pass quantum information along, you have to move down this axis because the only way in or out of this impossibility sphere here is to follow lines at this point because you can't really do anything except just quantum tunnel or move down the line, right? So you can quantum tunnel and then all of a sudden you're in the next dimension, or you can move down the line. There's 2 ways you can do this. So yeah. Uh, so the idea is that yeah, this is going to be superposition and entanglement. I think that the quantum tunnel might be. I don't know. It's fine. We'll have to figure out which one it is a little later. Now, I was going to draw the lines because there are lines that lead you inward here. And these are in fact the lines that we can follow. Should they they should all be black lines. Let's make them all black here. Because the idea is we're just following. I think they come from all different dimensions though, so that's the thing. So that's why they kind of curl inward. So once they curl inward, weird stuff happens. So like, you know, you need a lot of different dimensions to curl inward. So let's just kind of separate all this stuff. And these are gravitational flux lines, essentially. And these are the only things that are leading in now. So essentially, the information can either move inward through one of these lines from one of these dimensions that are heading into it. So here we are, just kind of ticking along, So shift through here, and then you can quantum tunnel to another point, maybe, and then you can sort of shift back. So that's the key, is that you have to sort of be affected by that next dimension to be able to come back to this line. You can't just go to the next step. You need to come over here to some other dimension, and then you'd have to come back. And it took time to do that. So now I have to quantum tunnel, and now I can go back here. Follow this to the last bit. Notice how these particular things are supposed to increment as we go along. So be very careful that they would start. Um, these things change as you move them. So the idea is that it causes acceleration or deceleration. Let's just go ahead and mm, so this is how we can sort of see that maybe there's acceleration here, or if, you know, there's time and space could be separated by this sort of need. The quantum tunnel over here, and the reason it has to stop is because these are zeros. So the zeros mean there's never ever going to be any one in that point. So you kind of have to like stop for a second there, and then you can move to the next dimension. And you can come back if you want to, but you can't just move straight down the line. That's not really quite going to work. So you have to step down the eigenladder. This is the eigenladder. As you can see, these eigenvalues seem to be essentially changing distances. So each graviton can sort of be quantized by using the sort of, there's some quantum number associated with it, which I think is we're heading here, is that the zeta zero. Um, so essentially each one of the zeta zeros uh, encodes a different value here. It's generally going to be that 1/2 plus I t, make that z, where these are the zeros. Sort of actually, it makes sense to call it time, because maybe it's really time that's shifting through there or something. Obviously, time and space are the same thing, so, you know, maybe those tunneling through dimensions is what time is, quantum tunneling. Through the dimensions. This is quantum tunneling info to the next dimension. Is causing this time here. So, hmm. And this is kind of where it's heading towards. That you might be able to use these unique zeros as potential nodes in this zero energy zeta spin network, where you can kind of form this filament of zero energy and project these nodes across infinite dimensions and just it makes different shapes and stuff. So obviously this is the ideal unique shape here that kind of is a linear transformation at the golden angle. And so this is the highest entropy, highest entanglement, lowest energy path. It's just nice, neat, organized. Everything's perfect. But unfortunately, those are the stable quantum nodes, always at zero. So like these are the zero nodes. And so then yeah, you can activate energy at other points, just not at those. So uh, that's kind of where we have this energy that's going to spread, across all other values. And you normalize that energy in some kind of a linear combination. Um, that linear combination could include zero. But yeah, these are the possibilities and these are the impossibilities. I think this is kind of where quantum gravity is starting to go towards. Quantizing sort of the distances between the zeta zeros. That's not really possible. So this is kind of like the quanta of gravity here. Is the distances between the zeta zeros on the critical strip seem to be a quanta of gravity. Just double check something real quick. On the critical. Okay, perfect. So yeah, the distances between the zeta zeros seem to be this quanta of space, which can't be quantized because each distance is unique. So space, unique distances. Unfortunately, they're unique distances between the zeta zeros, so they form the quanta of space. The impossibility sphere. Now it's unclear whether the inside of the sphere also contains full sets of zeros, or whether the information inside is still flickering. So that's, inside. We don't, that might be a little harder to figure out. But on the outside, I mean, it kind of makes sense that the inside and the outside would kind of, um, would function the same way, because this is just what we know is here in space. But, there is a way to quantum tunnel outward and back out, because the only way inside is through the lines. You follow the lines. Well, that's one way inside. Obviously, the other way inside is also the quantum tunnel, but that would suck. So the idea is the quantum tunnel outside. That would be better. Yeah, so you can quantum tunnel outside. And if you manage to quantum tunnel outside, the quantum tunneling inside would suck. But quantum tunneling outside, that would be good because then you've escaped the black hole. You see, and that's Hawking radiation. So this is some interesting stuff here. Um, so one reason why the strip is ideally straight, linear, is that way you can continuously make transformations, and you get to the end here, and everything's still straight lines. Um, that's kind of the ideal thing. It's still straight. You can continuously make transformations forever. In fact, that's nice because this helps to let time go forever. We don't know if that's really the case, but it might actually be. Maybe, maybe. It's quite possible that time has an end because time seems to have a beginning. Right here, all zeros converged. All zeros converged. That means that all zeros were at the same quantum, no longer unique zeros. In fact, no unique zeros existed at that point. Essentially, no quanta of space existed at that point. So nothing existed at that point. And so that was the beginning of time. Let's see if we can just kind of put this in, give us a little room right here. All right. So here we have the beginning of time. All zeros converged. That means that all quantum states uh, were zero. Well, like everything was zero. At the moment when there are no unique zeros. If there were no unique zeros, these unfortunately became really, really small values. This was starting to become really close to zero. No unique zeros. Right, zeros. These particular ones. And so this marks the beginning of time, where there was no space. So we have to like readjust this again. It's a little bit crazy, but this is kind of what these numbers are trying to say. We can complain, but I think that the numbers don't lie. Sometimes it's a little difficult to organize all the information. All zeros converge. We have no unique zeros. That means it's the beginning of time. Time can keep going on forever if we keep making unique zeros. That means there's a new set of zeros. All zeros diverge means that, again, there are no unique zeros, but this apparently seems to be those singularities again, where, well, there's too much quantum information. Those numbers are just too big, you know? So all zeros are diverging. There are no unique zeros anymore. And then it keeps going forever. If you can make new zeros, um, and if there's a beginning of time with no space, this kind of implies that there was no space, as in no distances between the zeros. Same thing here as well. No space, no distance. We'll call it delta z, or really delta t, I guess. We'll call it delta s, right? I don't know. Between the Riemann zeros, you know. These are those, and same thing happens here. It's kind of no space here either. Uh, Possibly, or maybe the distance between the spaces are just too large, and delta s could be just insanely massive. Or it's not the same thing. There's a freaking look at the sizes of these things. Possible that the distances between the zeros get too large. This is kind of where the distance becomes infinite. Hmm. Yeah, maybe it does become infinite, meaning, you know, if you're kind of here and you're sort of trying to get into the middle of this black hole, right in the middle, inside there, uh, it might just be like infinitely far away. It's like you'll never reach there because the spaces are just too far. The distances, all the zeros are diverging. But yeah, I don't know. It's getting a little bit crazy here. So we're ticking down the eigenladder. So we're just going, and then we're quantum tunneling, and then we're going a little further, quantum tunneling, a little further, quantum tunneling, and so we're sort of accelerating with each step, quantum tunneling, accelerating with each step, and sort of getting closer and closer towards these gravitational spheres, I suppose. Just a curvature. We're following the curvature. The curvature may be really, really strong and create these. Uh, Essentially, we're folding over the zeros of this strip, is how we're doing this. So we're curling the critical strip into a circle instead of a line. And then after that, we are basically wrapping this out, curling this around in infinite dimensions. Like that. How can I put this? We're filling in we're basically all of the unique zeros are interfering to fill the entire circumference of the circle, which is the axis, in just one dimension. And then we just have to basically rotate this around into a little sphere of zeros. Rolling the critical strip into a circle. Well, consider again, we have infinite dimensions, and a sphere, and then again we have infinite dimensions in the 2 pi area, right? 0 to 2 pi is another place where we can find infinite dimensions. These infinite dimensions, these are the transformations. Transformations, these are the transformations. And what I mean by the transformations again were these particular transformations. As you can see, there's ways to wrap the zeros around and change their lengths and sort of put them in between each other if you sort of line them up together. Well, you could wrap this around infinite dimensional transformations. And so now you have all the zeros interfering, fills this entire circumference of that circle. Okay, and then we can go from 0 to 2 pi in order to gain more infinite dimensions, essentially, but we're essentially making a sphere. Here's the 0 to 2 pi. It forms the impossibility sphere. Transformations. All right. So yeah, I think we have quantized gravity somewhat. This may or may not be finished because we don't know everything that's happening inside the black hole. We might be able to try to figure that out, but essentially we've kind of come up with ways to transfer quantum information from one thing to the next, through this sort of zeros and ones, only zeros and ones, and we can sort of move from the you know highest energy level out here, highest energy level. So essentially we just have high energy, and then we can go down to the lower energy, which is exactly um, what all quantum systems want. All quantum systems want to go from high energy to low energy. high energy. We mean more like um, it's just it's a further spacing, so the gaps are bigger. It's this is interesting what we're finding here. Well, I'm gonna go ahead and try to look into this a little bit more. I think all this stuff kind of makes sense. Let's not forget though that all this information can essentially be encoded into this universal K vector. So we have any property can be lined up as this linear combination as long as it's yeah, any property. And so you can toggle the properties and then you can do transforms between any property spaces and represent any information uh, by using zeros and ones. And not necessarily, I mean, obviously all the other information is still there. It's just that we had to normalize it. So we normalize things to the point where all the probabilities can just be 1. So that way you get 1. So you have whatever information you want and just, give it a possibility, a probability, normalize it, and then present that any number of dimensions. Just go ahead and flip those switches, and then we can go ahead and go back to the unique zeros here. These are never going to be 0. So, I just kind of and yeah, this is just a pretty easy way that you can kind of switch from classical coordinates to quantum coordinates. This is pretty fun stuff, but I do have to run tomorrow, so you know it's a bit of a bummer that I kind of have to call it a day. I've been working on this for a while, and these things are starting to sort of emerge, these explanations for these numbers. Sure. Zeta. Yeah, thanks for checking out the video and stuff. This is kind of difficult, but you know, we don't really know. I don't know if there's a proof here, but it seems that once we kind of get towards this black hole surface area, and the quantum effects can kind of be explained there, that's kind of nice. Uh, yeah, so y'all have an awesome night. I'm gonna try to try to get to class at super early tomorrow morning.